Welcome. This is an extra video. No exit ticket is required for this video. Basically, I will review with you some of the basics of dimensional analysis and unit conversion. And then after this, we will look at your homework problems and I will give you some hints on how to solve it. Yeah. Physical dimensions, like there are uh, physical dimension, primary dimension about like so there's like mass. So this primary dimension are mass, length, time. There is also temperature, and there is mole, also like units counts. But here we will mainly focus in this course. We will mainly focus on mass, length, and time. So this is our primary dimension, and from this primary dimensions, basically you can drive other dimensions like secondary dimension, like for example like water storage. So water storage could have a unit of, for example, like a meter cube or like feet cube. Yeah, water storage, or kilometer cube. Yeah, or mile cube. Yeah. But all these are the units, but the main dimension here, what like length and to area would be like length square. So this is length square area, and volume would be length cube. So it will be like L cube. So the dimension of any water storage of like this guy, this guy, this guy, this guy, the dimension of this guy is like length cube, because you have a length and then length give you a volume, which is like meter cube, feet cube, kilometer cube. Flow, for example, what is flow? So flow rate, this is volume per time. So this is like flow rate, this is volume per time. And what is the dimension of volume? That is like L cube. And what is the dimension of time? That is T. Yeah, so it could have like the dimension of T. So flow rate, the dimension of flow rate is L per time. The unit could be anything. The unit could be like meter cube per day, or meter cube per second, or I don't know, feet cube per year, whatever. Yeah, so that are the dimensions. You need to differentiate between, sorry, the units and the dimension. So the dimension would be like length cube over time. Why? Because this volume has the dimension L cube and time is T. Velocity, what is velocity? So velocity, that's like distance over time. So distance, that's L, and time, yeah, over time. That's the dimension. The unit could be anything. It could be meter per second. It could be a mile per hour. Speed like 70 mile per hour, whatever. Yeah. Could be kilometer per hour, like 100 kilometer or 120 kilometer per hour, or what. I mean, that's the unit, and the value would be anything. Yeah. Meter per second, but the dimension is length per time. So, so that is so any unit dimensional analysis basically will help you to like in dimensional analysis any like equations, yeah, any physics-based equation, it you need to have the dimensional homogeneity, like on the left hand side and the right hand side. So for example, let me give you an example. Like I will tell you force is equal to mass time acceleration. The dimension of this guy should be equal to the dimension of this guy for any physics-based equation, not empirical equation. Empirical equation could be different, but any physics-based equations, the dimension should be consistent. Yeah, they need to be homogeneous, consistent. So let's do this. Yeah. So what is force? So force is uh, what is the dimension of force? So force is like a mass like time acceleration. So force, that is mass. So that would be m. And what is the acceleration? That is L over t square. Yeah, because that is acceleration is velocity over time, and velocity is like distance over time, so that will give you like distance is time square. Yeah, that's like L square. So that is the unit of force, dimension of force, and that is here would be the same, m L over t square. Let's look at another example. Volumetric flow rate is equal to velocity time area. So this is continuity equation. Yeah, yeah, I think so. Yeah. Volumetric flow rate is like velocity time area. For any quantity, calculate, write its unit unless dimension slope. Okay, so this is, we know Q, this is volume over time. So volume is L cube over time is equal to velocity, that's like length over time, and area, that is like L square. So you got here L cube over time. So L cube over time is equal to L cube over time. So basically, any equation you solve, you need to check this dimension and to make sure that it is dimensionally consistent. That is how uh, you will know. And some other quantity, for example, slope, that is m over m. So this one would be like dimensionless. We write it either dimensionless, or you can write it like this, L over L. Both are correct. Like either dimensionless like this, or this would be also understand like uh, dimension. Now another thing is equally important as dimensional analysis is the unit conversion. So we can divide apple by oranges or anything like this. So you need to make sure that the units are consistent when you do calculations. So for example, like mass, it could be in gram, it could be in kilogram, it could be in slug or pound weight, or it could be in ton. Yeah, so pound mass is like slug. Length could be in meter, it could be in kilometer, it could be in inch, feet. Year time could be in second, hour, the year, 10 years, whatever. Yeah. So if I told you what is the storage, and I want the storage not in mile cube, but in inch cube. So how can I solve this? So I have this. So this is my area. So this like my catchment area is 11 miles. So I have a catchment which is like 11 mile, and then I have 12 inch of water. Yeah. So this is like 11 mile, and this is like here, let's say like 12 inch of water, and I want to see like the volume storage in inch cube. Obviously I need to convert this mile to inch because I cannot multiply apple by oranges. So how to do this is easy. I mean, there are many ways of doing it. I like to do it uh, not like, how can I say this, like I like to do it explicitly, write everything so that there will be no room for doing any mistakes or for confusion. So what do I want to do here? I want to get rid of these miles. Yeah. So I want to get rid of these mile. How do I get rid of these miles? So I want this to go away with this. So basically I know that like 1 mile cube is like 1 mile length is equal to 5,280 feet. Yeah. So 1 mile cube, this is like would be like this guy times this guy. Yeah. Because you get here feet cube and this here. And this will go away with this because 1 mile is equal to this and 1 mile is equal to this. 1 mile square would be equal to this. So basically like this one and this one. So here now, when I did this, I could cross this one with this one. But I don't want this in feet. I want this in inch. Well, it's not a problem. Why? Because I know like here I want to get rid of this feet and make it like into an inch. Yeah. It's not a problem. Why? Because I know that like 1 feet, yeah, has like 12 inch. So like the if this will go away with this one because 1 feet has away with this inch, so this one will give you 1, yeah? So now I can get rid of feet, but I have two of them. I have feet here and I have feet here. So then I do it two of it because again, like this is one and this is one. But now here, I was able to get rid of this feet, will go away with this guy. This feet will go away with this guy. So basically what I ended up with, I ended up 11 times 528 times 528 times 12 times 12. This is equal to uh, uh, 15 inch, so it takes 10 to the power negative 11 feet inch cube, or you can even simplify it like 6.6, not 6.6, yeah, 10 to the power 2, yeah, billion. So this will be like billion inch cube. Or you can even simplify it more like 660 billion inch cube. Yeah. So that's like 6.6 billion inch cube. Yeah. This will give you this number. Yeah. So that's like if you want to simplify it further. Okay, let's do a class exercise. Let's do this exercise together. And outdoor, I mean, try to do it, and then like it checks the answer. So please pause this video, try to do it. If you can do this, then you should be okay. Why am I giving you this? Because I noticed that some student they make these types of mistakes. So I don't want you to lose grades because of these like very basic mistakes. And I will show you like other types of mistakes that the student also I've noticed that they do. But after this exercise, an outdoor swimming pool is 12-meter long and 5-meter wide, and the pool has water all the time. If the weekly evaporation is 2.5 inch, how many gallons of water is evaporated every week? Yeah, okay. So how many gallons of water is evaluated all the time? And the weekly evaporation is, so this is how much water get evaporated each week. How many gallons of water is evaporated each week? So basically, I want to calculate like evaporation, but I want to calculate like evaporation not in inch, not in so like not in inch cube, not in meter cube, but in gallon. Yeah. So what can I do? So let's first calculate the area. So like the first part, I will like just do, I will say like the area. So I have 12 meter times 5 meter. That will give me like, and you can here also you can look at significant figure 12 meter times this one, and this will give you like 60 meter square. Yeah. Uh, okay, so now here I have like three significant figures in this thing. So now let's do the evaporation, like how to do evaporation. So the evaporation, I'm getting like, so evaporation, I have 2.35 inch per week. Yeah, so I have 2.5 inch per week. And then now what do I want to do? I want to convert this to like meter. Yeah, I will keep this meter. I want to convert this to meter. So how can I convert this to meter? Well, how could I convert this to meter? Can you tell me how to convert this to meter? So to convert this to meter, I need to have something like inch here and meter here because that's how I will get. So I want to see like 1 inch has how many meters. So 1 inch has how many meters. So you can Google this. You can say like, or you can use like a textbook you have or whatever. But so I can just come here and say 1 inch equal to how many meters. So that's how many, 0.0254. Yeah. Okay. So 1 inch is equal to 0.0254. So now I can get rid of this guy. I can get rid of this guy. And then if I multiply these two together, I will get 0.05969 meter per week. Yeah, because here that's like meter per week. Okay, so good. So now I have, this is the area. And this is the evaporation rate. So now volume evaporated. So like the volume, if I want to see like the volume, vol, volume evaporated, that would be equal to what? That would be equal to the area times the evaporation rate, like from this area per week. So here, that would be the evaporation rate, 0.05969 meter per week. So that's per meter. How many meters do I have? I have like 60 meter. So I will get, if I multiplied this together. So here meter times meter squared is like meter cube per week. So I get 3.581 meter cube per week. Evap 8584. You can put as many figures as you want. Okay, so now I'm getting, this is how much evaporation I have. So each week from a 60-meter pool, you lose about 3 cubic meter of water per week, yeah, giving this evaporation rate. But actually, some of you might not be familiar like with this matrix system. You'll be more familiar with gallon, like how many gallons. That would be a unit because here, yeah, we don't like you don't buy milk here in the USA by liter. You buy it. So each meter cube has 1,000 liter. You don't buy it by liter. We buy it here by gallon. Yeah. So let's convert this to gallon. So how can I do this? Again, uh, I have like 3.5814 meter cube per week. What do I want here? I don't want this to be meter. I want this to be gallon. So I will say like 1 gallon has how many meter cube? Yeah, because now the meter cube will go away with the meter cube, and then I will have gallon per week. So 1 gallon has how many meter cube? Again, you can go here and you can say 1 gallon to meter. So 1 gallon to meter, uh, one like sorry, I mean I did the mistake here. It's not, this is like here, this is 1 meter because I want to get rid of this. So this is 1 meter has how many gallon, not the other way around. Like 1 meter has how many gallon? Yeah, because this number we got is very small. Like if we could calculate it here, that wouldn't work. So basically, like here, like if to get rid of this 1 meter, so I get like 1 meter. Oops. 1 meter here will go away with 1 meter here, but gallons. So you go here, 1 meter cube to gallons. Yeah. So 1 meter cube has 26 like this number. Yeah. 264.172. Yeah. So that it would be equal to, so you put here time and you put here 264.17 gallon. So if you did this, yeah, you multiply like this guy with this guy, you can use. So again here now, like this meter will go away with this meter, and then you'll get gallon per week. So you get 946.098 gallon per week. Yeah. So now, like here, we want this to be like with now here. So that's basically you will get you will get you will get like this one. And now if you want to have this with here, how many significant digits should we have this? So here we have like 3 significant figures. Here we have 2 significant figure. Here we have 3 significant figures. So basically you need to express this with only 2 significant figures. So with 2 significant figures, you will come here. So you have like 1, 2, and then this is 6. So you round this to the next one. So if you want to express this in 2 significant figures, you basically do it something like 250 gallon per week. And you can learn, like you can watch any YouTube video on significant figure, like how many significant figures to use. But because like usually you do the minimum one. So here like 2 significant figures, 3 significant figures, here like 3 significant figures. So you express it with like 2 significant figures. So 2 significant figures, so like 1, 2, 3, like 1, 2. And then like, so you ignore all this, and this you round it up. So this will round to 5, and then that would be 0 and gallon per week. So that's like 2 significant figures. Yeah. I'm expressing with the minimum significant figures that I have here. Okay, so this is basically some exercise. Now let's look at your homework. So let's look here at your homework, and let's try to solve this homework together. Yeah, I'll just give you some hints on how to think about it and how to solve this homework. So let's apply what we learned. So this problem is from the Contaminant Hydrogeology book of Fetter. And let us consider a groundwater basin that has a surface area of 100 kilometers. So now this is a groundwater basin. It has a surface area of 100 kilometer, 125 kilometers square. The groundwater basin is the surface volume through which groundwater flow toward the specific discharge zone. So like stream. So this is like a groundwater basin. Okay. And this area is 125 kilometer and cube. And then there is like a stream here. We don't know like about this stream, like, but like the groundwater will discharge. So groundwater basin means that out of here. Yeah, it's all impervious. It's like a groundwater divide. So it means that groundwater will only discharge will only leave through surface water. So here you have like kind of like base flow. Yeah. And that's how you think about it, yeah. So here water, is base flow. In other words, there is no ground flow either in or out of the basin. The basin has a stream, headwater starting from the basin. So the stream starts from the basin, so it's headwater. So the stream does not so the stream start here at the basin, yeah, headwater at the basin, and flow out to the basin. So like the base flow, so here you have a stream outflow, stream inflow because it start here in the basin. There is no surface water from the stream to the groundwater. So the base flow is only, there's no stream outflow to the groundwater. Yeah. In other words, the stream is a gaining stream. So this is a gaining stream. You just take base water, base flow, but it's not a losing stream. It does not lose any water to the groundwater. We assume that the stream is narrow and that the precipitation to and evaporation from the stream is negligible. So basically, like any evapotranspiration or precipitation or the stream is negligible. Stream like if this is the basin 100 kilometers square, the stream would be what, like few meters. You wouldn't even see it here. It would be just one line. So the stream would be just line. So that's why, because like if this is even 5 or 10 or 20-meter wide, it is negligible compared to 125 kilometers square. Yeah. This is kilometer square, not cube. Sorry. It's kilometer square here. Yeah. So you have bottom stream and then you have a stream outflow. Okay, assume that the stream is narrow and precipitation. Okay, the following long-term annual average has been measured. So precipitation in the entire basin, so P is equal to 60.3. Evapotranspiration from the entire basin, ET, is 46.3. So here, what is your input? So your input is P, you have precipitation. Your output is AT. Yeah, you have evapotranspiration. Yeah, overland flow to the stream. So you have like a base flow, you have overland flow to the stream. So this is overland flow. Overland flow to the stream. So we have overland flow to the stream. That is like 3.4. So this is all in centimeter, centimeter, centimeter. Yeah. Base flow to the stream, like this base flow here. So you have overland flow to the stream. Flow is like 10 to the power 0.6 centimeter. Yeah. Okay, now what is this question asking us? Now here, this is a whole system, but remember, when you make a water budget, you can make it for all the catchment or for each individual component of the catchment, and this will be different. You first, then after you delineate your system, you find the input to this system, you find the output to this system, and then you find the change in storage to this system, which is B. So change in storage is equal to input minus output. Yeah. But let's see what is this asking us to do. Water budget for the basin as a whole, listing input in one column, output in another column. Make sure the two column balances as this are long-term value and we assume no change in volume were stored. So basically here the S is equal to 0. So input minus output is equal to 0. Yeah. So how to do this? What would be the input and what would be the output? And again, here the entire basin. Yeah, I'm not considering entire basin. So the entire basin, what's happening in this entire basin is simple. Uh, Everything's like, let's start with the input. So what is the input? So the input to this basin is precipitation. Yeah, the input is precipitation. What is the output? The output of this system is ET. Like you have precipitation, you always have like ET. What else? It is stream outflow plus stream outflow. Is this like an output, like the base flow from groundwater to the stream? No, because this is something that's happening internally. Is this an output over land flow to the stream? No, because this is something that is happening internally. But so what is exiting this system? Because remember, you delineate your system. My whole system now is this guy, like the whole catchment. So what is entering this catchment is precipitation. Water is only leaving this catchment through evapotranspiration and through this thing. Yeah. So let's see if we will balance. Yeah. So in one column, let's look, which is 40.3 plus the stream outflow. So are we giving here base flow to the stream? So what is the stream outflow? So we can calculate this. So this is the stream outflow. What is the stream outflow? So the stream outflow basically is two component. What is this stream outflow? So the stream outflow is the stream gets is land overflow and base flow. So that's the stream outflow. Stream outflow on water and over land flow. So base flow from groundwater, that is like 10.6 plus outflow, that is like 3.4. And if we did this, so what do we get here? So we get here 11, we got 14. Yeah, so we get 14. So basically, if you added like this guy to this guy, 14.3, because the outflow is ET, so this is like your ET, and the outflow is your stream outflow. Stream outflow, that's 14. So if you added this one and this guy, so that will give you 60.3. Yeah, so we made the balance for the entire catchment. Okay, what's the second question? Water budget for the stream. In other words, what are the inflow and outflow to the stream? So that is easy. We did this already. Yeah. So the stream, the outflow to the stream, we know this already. The outflow to the stream, we know like that stream, you have like the input to the stream is input to like the stream. That is like the base flow and overland flow. The output of the stream is like the stream outflow. So can we prepare this water budget? Yes, we know. So we know like stream outflow, that's equal to base flow plus overland flow. So that will be what we have here, 10.6 plus 3.4, that will be 14. Yeah. So that would be this one. Yeah. Yeah. So basically, like if you look at this, that will you will get 14 here. Yeah. And this is all like, don't forget the units. This is like in centimeter. Everything in centimeters. I'm not putting the unit, but you know everything is in centimeter. Okay. Now let's read our budget for the groundwater basin. Okay. So like, what is the like annual water budget for the ground? Annual water budget for the groundwater basin. So now like the entire basin, like this is the entire basin, but I'm just like looking at the groundwater basin. So the groundwater basin, what do we have? So the groundwater basin, basically you have like input and you have like output. Yeah. So the output we know that is the base flow. That's the only output. What about the input? So the groundwater basin. So the input, basically, we know that there is no. This is the stream does not feed the groundwater. So we don't. We know that this is not occurring. But we have infiltration. So the input to the groundwater. This is the output of the groundwater. So the output of the groundwater is base flow. The input of the groundwater is what? Like in filtration, like infiltration. So basically, or like recharge, it's like recharge, yeah. So So basically like recharge. And what is recharge? So recharge, remember, is that what is recharge? So like you will that would be like the recharge that is coming to uh, like the recharge that is coming to the groundwater, and that would be what? That would be the what will infiltrate from this precipitation. So like you have precipitation, yeah, and this precipitation you will have, let me see, like infiltration. Like here, that would be infiltration. Yeah, input, that would be like, I will call it like infiltration. Yeah, I don't know, maybe I will call it like infiltration to differentiate it from this one. So you have infiltration and you have like, this is infiltration. What is this infiltration? Like remember, this infiltration is precipitation. So you have like precipitation. What will happen to this precipitation? Precipitation is equal to 1. So precipitation, that is equal to evapotranspiration plus overland flow. So this infiltration basically it would be equal to, like you have precipitation, part of it will be ET, part of it will be overland flow, and the rest will be infiltration. Yeah, like you have precipitation, part of it will be ET, part of it will be overland flow. And what would be the remaining part? The remaining part would be like infiltration. So infiltration is equal to precipitation minus ET minus overland flow. So let's look at this one. Infiltration is equal to precipitation. So precipitation is giving like 30 point what? 30.3 minus ET. What is ET? 46.3. 46.3 minus the overland flow 3.4 minus 3.4. So if you did this, like you did 60.3 minus 46.3 minus 3.4, that will give you like 10.6 centimeter. And all this is centimeter per year, yeah? I'm not writing centimeter. Everything here is centimeter per year. I'm just writing this for simplicity. So this give you the this guy is basically the infiltration over, and the output would be like the base flow. That would be the groundwater budget for the groundwater basin. And what is the base flow? Let's check. So the base flow should be 10.6, yeah? Is it 10.6? Yeah, exactly 10.6. So exactly right. So here for the groundwater system, we have like infiltration, yeah, would be equal to base flow. So you can write it in this way, or you can write it more explicitly, like infiltration, that's like precipitation, negative ET, negative uh, overland flow, that will be equal to the base flow. Yeah. So basically that is how you system. Yeah. Now let's look at one more. What is the annual runoff post stream and groundwater from the basin expressed in centimeters per year? So what is the annual runoff post stream and the groundwater fill runoff? Do you remember uh, what is the annual runoff post stream and ground the stream outflow? That is 14. Yeah. So we know this is, we did this already, like this. So remember what is runoff? Runoff is overland flow, uh, uh, the flow from vado zone to your stream, interflow and base flow. So basically, what is the runoff? We don't have interflow. We only have, so the runoff. So it's basically annual runoff. So the runoff, that is equal, remember it was equal to base flow over land flow and interflow interflow, that's from Vado zone, so that is equal to 0. So base flow is giving as like 10.6 plus overland flow. I would say this is 3.4 because we just, yeah, overland flows as 3.4. So that will give you like 14 centimeter per year. And this is exactly 14 centimeter per year. And this would be the annual runoff. That would be, we calculated this before, 14 meter per year. So that would be the runoff, or so remember, like we can call this runoff, or you can call this stream or outflow, stream outflow or runoff or total runoff. Okay. So this is what is the annual runoff from the basin expressed as the average rate in cubic meter per second. So the volume of runoff. So basically, like I have this volume of runoff. So I have like this runoff is giving to me in centimeter per year. And it's telling me now I want this not to be in centimeter per year, but like meter cube per second. Like, okay, so how to do this? Like, let's do it again. Again, that's a good exercise. It's a good practice for your homework. So how to do this? So what do we need here? We need to change the centimeter to okay. Uh, uh, this is like we need like this is a runoff. We need to change this centimeter to meter, and then we need to find for the entire basin. So that you need to multiply like so. This is centimeter per year. This is just like so here. This is the basin 125 kilometer and this is just like here's centimeter. So we need to convert this to meter. We need to convert this to meter in order to get something at the end in terms of meter. So basically, this is what I have. So how could I convert? And we need to convert the year to second. Yeah. So we have a lot of conversions to do here. So let's do it. Yeah. So the volume like volume per time. So that's the Q we are interested in. That would be equal to the runoff time, like the area. Yeah. So the runoff uh, that would be 14 centimeter per year times the area. That would be 125 kilometer square. But we cannot multiply this anyway because this is in centimeter and this is in kilometer. And we want the final answer to be in meter, not in kilometer. And we want the final answer to be in second, not in year. So that's easy. Yeah, let's do it. So centimeter, let's get rid of the centimeter first. Yeah. So how to get rid of the centimeter? I know that like each 100 centimeter has like 1 meter in them. Yeah. So now I get rid of the centimeter. How do I get rid of the year and convert this to second? Well, to get rid of the year, I need to put like, I know that like 1 year is equal to what? Like 1 year is equal to 65 days. Yeah. Time. Each day has like 24 hour and each hour has like 60 minutes and each minute has 60 second. Yeah. So now, so I know that like 1 year has this much, has this amount of seconds. So now I was able to so like this guy will go away with this guy will go away with this guy. So I will end up with meter per second instead of centimeter per year. Okay. But I have another one to do. Yeah. I have this guy like, so time 120 kilometer square. So how to do this guy? So I know that like I want to get rid of like I know that like one kilometer, and then you can square this, yeah, is equal to 1,000 meter and then you can square this. Yeah. So now this guy will go away with this guy, and I will end up with meter cube. So if you did this, you will end up with something like 0.555 meter cube per second. About half a meter cube per second get discharge from uh, would be like the runoff of this homework one, like the water budget. So this will help you to solve homework one. Okay.